Okay. Hi everyone, this is Ayatya. We are group 19. Today I have my team members Giridhar and Nanda with me. We will be discussing present reading material 5 today. Mastering the game of Go with deep neural network and research will be our topic for today. Game of Go is one of the most classic challenging games for artificial intelligence spectrum. It is complex because it has huge data space that we need to evaluate when we are working with the algorithm. In this paper, the authors are introducing a new method of the Go game using the virtual network to evaluate the position and policy network to choose the move. All games with perfect information have an optimal value function. We can refer it as B star, which will compute the outcome of the game. These games are usually solved by using the optimal value function recursively in the tree search. Counting the possible sequence of the moves, which we can denote as B in the formula. B usually determines the game's breadth, which means the number of legal moves we can take for the position, and D denotes the game length. Usually, deep neural networks are trained by original combination of the supervised learning from human expert games and support learning from games of self-play. This paper also introduced new search algorithm that combines Monte Carlo simulation with the which we use the value policy network. This will be first time that a computer program wins over human professional player during the Go game. In that game, champions wins 5 points over zero for the opponent. They have trained neural network using the pipeline consisting of the several stages of machine learning. Let's move to the next slide. So here we will discuss chess and the complex Go game. To reduce the search space, we can actually truncate the search tree at a state S and replace the subtrees by using the value function. This approach will be led to superhuman performance in chess and checkers and Othello, but it will not successful in the Go game due to the large search space we have in that game. Monte Carlo rollout search maximum the deep depth without branching by sampling a long sequence of action for both players. So there are two main ways we could use to reduce the search space. First one is depth of the search may be reduced by position evaluation. The second is sampling action. So we can reduce the breadth of the search by reducing the sampling actions. Policies are usually used to narrow down the search to have high probability actions and simple the doing the rollouts. And next, we will be discussing supervised learning of the policy network. At the first stage of the training pipeline, they have to build the pre-work on predicting the expert moves in the game of Go using the supervised learning. In this figure, neural network training pipeline, rollout policy and supervised learning policy networks are trained to predict the human expert moves in data set of positions. In reinforcement learning, the policy network is initialized to the supervised learning policy network and then improve the policy gradient learning to increase the outcome. Even if we take a small improvement in accuracy, that can be led to the large improvement in the playing strength. If you look at in the figure B, we can clearly see that. When the network is larger, it achieve better accuracy, but it can slower the so the evaluation. When we go to the next, the second stage of the training pipeline, that will be reinforcement learning for policy network. It focuses on improving the policy network by using the policy gradient trains reinforcement learning. The policy network take representation of the broad positions as its input, and then it will pass through many layers of supervised learning policy network and reinforcement policy networks. The value networks use many conventional layers with the parameters in order to populate the scalar output. When we play the game between current policy network and random selected iteration of the policy network, we will be doing that in a randomized form to pool randomized pool of the opponents, so it will not cause any overfitting. If we go to the next step, which is the final step, that will be final step of the training pipeline is position evaluation, estimating value function that predict the outcome of the position of the games played by using the policy P for both players. In order to perform well, we need to identify the optimal value function under the perfect play in practice. Instead of estimating the value function, we could use reinforcement policy network. It will approximately use the value function using a value network with some weights. This neural network has similar functionality as policy network, but it will output the single prediction instead of the probability of the distribution. And here the searching with policy and value networks, the AlphaGo combines the policy and the value networks in MCTS algorithm, which will select the actions by look-ahead search. Each edge is evaluated two ways, using the value network and by running a rollout to the end of the game, which first with fast rollout policies. The tree is traversed by simulations and starting from the root state. When traversal reach the leaf node, supervised learning at the step 1, then leaf node may be expanded. So leaf node is processed by supervised learning policy network. And also leaf node will be evaluated in two different ways, such as value network and outcome of the random rollout played out until we reach the termination step. And also here we will be discussing the evaluation of the AlphaGo game. In this diagram, we can see the result of different tournaments between different Go programs. Each program uses at least five computation time per move. Evaluating the policy and value networks requires several orders of the magnitude more computation than the traditional search heuristic. AlphaGo also uses asynchronous multi-thread search. In diagram B, we can see performance of the AlphaGo single machine for different computations of the components. And the diagram C, we can see the scalability study of MCTS in AlphaGo with the search ahead and GPU is going to be a synchronous search or distributed search 2S per moves. In order to evaluate AlphaGo, they have ran the international tournament among the various variants of the AlphaGo, and then several programs such as value network, tree evaluation, and tree evaluation for rollouts. So next point onwards, my team member Giri will continue.
Thank you, Ayodhya. Now I'm going to discuss about the mastering the game of Go without human knowledge. A long-term goal of artificial intelligence is to make an algorithm that can learn from scratch to be very good at things that are hard for humans to do. In recent years, AlphaGo became the first computer to beat a world champion at the game of Go. Deep neural networks were used to look at positions and choose moves in AlphaGo tree search. These neural networks learned how to move by watching humans who are good at it and by playing with them on their own. Hence, we show you an algorithm that only learns by playing games. It doesn't use any human data, guidance, or knowledge of the game rules. In this case, AlphaGo is its own teacher. A neutral network is trained to predict AlphaGo own moves and the winner of AlphaGo games. The neutral network improves the strength of its research, which leads to better move selection and better self-play in the next iteration. When we started from scratch, our new program AlphaGo Zero performed like a real person. Our program AlphaGo Zero is different from AlphaGo Fan and AlphaGo Lee 12 in a number of important ways. In the beginning, it learns through self-play reinforcement learning without any help or use of human data. Second, only the black and white stones on the board are used as input. When it comes to the third thing, it doesn't have a separate policy and the value network. Finally, it uses a simple tree search that doesn't use Monte Carlo rollouts. It uses this single neutral network to evaluate positions and the training loops. This leads to the quick progress and precise and stable learning. The method explains more about how the such algorithms, training procedures, and the network architectures are different from each other. Next slide. Our new method is based on the deep neural networks that has parameters. There is a neural network that takes a raw representation of the position and the history as an input. It then outputs both move probabilities for the position. The vector of the move probabilities show how likely it is that you will choose each move. Value V is a scalar evaluation that estimates how likely is that the current player will win from position. People who work with policy networks and the value networks can use this one system to do both jobs. This is how the neutral network works. It has a lot of residential blocks of convolutional layers with batch normalization and the rectifier non-liabilities. And in the next slide, um, S1 to S6 are the games that the computer plays against itself. Each time an MCT is done, the most recent neutral network is used. People are moving selected by the MCT based on how likely it is that they will found at um, similar to the Pi 2. ST is the score according to the rules of how the game is played. So it gets a score. The parameters of the neutral networks are updated so that the policy vector PT and the search vector S are the similar as as a possible chance to make sure there isn't a big difference between who is predicted to win and who is actually going to win. Next slide, please. Self-play reinforcement learning. Uh, the gra- uh, The graphic depicts each MCT player performance in each iteration of reinforcement learning in AlphaGo Zero. To calculate the ELO ratings, we used assessment games between different players using the KGS dataset. A similar player thought using supervised learning from human data is also displayed. The MSE of the neutral network predicts that outcomes of human professional games at each iteration of the self-play. The MSE is the difference between the actual result and the neutral network value scaled from 0 to 1. The MSE of the supervised learning neutral network is shown in the above diagram. And in the next slide, and the
Yeah,
next slide, continue by Nanda. Thank you.
Yeah, thank you, Giri. And coming to these figures, total of a five figures, a five human common corner sequences discovered during the AlphaGo zero training, and the associated timestamps indicate the first time each sequence occurred, account of rotation and reflection as well during the self-play training, and extended data is shown in the figure 2. It provides the frequency of occurrence over training for each sequence. And in the figure B, five Jokosi favored at different stages of self-play training. Each displayed corner sequence was played was the greatest frequency among all the corner sequences during an iteration of self-play training, and the time step of that iteration is indicated on the timeline. At 10H, a weak corner move was preferred. At 47H, the 3-2-3 invention was most frequently played, as used in the AlphaGo Zero, and using either the convolution network architecture from AlphaGo Zero Li or the residual network architecture from the AlphaGo Zero. Each with residual network, AlphaGo Zero is more accurate, has fewer errors, and has improved performance by over 600 ELO. Combining policies and values in a single network slightly reduced the accuracy of travel predictions, but AlphaGo reduced value errors and improved game performance. And coming to the next slide, knowledge learned by the AlphaGo Zero, and the figure shows that the AlphaGo Zero how it is learned by using the graph. And finally, AlphaGo Zero endorsed the new Jokosi variant, previously unknown, and the figure 5C shows some quick self-play games played in the different training phases, and the tournament length games played at regular intervals throughout the training as shown in the extended data figure B, and in the supplementary information also. And AlphaGo Zero rapidly progressed from entirely random moves towards a sophisticated understanding of Go concepts, including Fugazi, Tisuji, life and death, Ko, usage, capturing races, sensitivity, shape, influence, and territory, all discovered from the first principles. Surprisingly, Shiko ladder captures sequences that may span the whole board. One of the first elements of Go knowledge learned by humans. We are only understand by AlphaGo Zero much later in training. And compared to the next slide, final performance of AlphaGo Zero, and figure 6b shows the performance of each program on the yellow scale, and raw neural network realized yellow without using look ahead rating of 3055. By comparison, AlphaGo Zero achieved a rating of 5185, and whereas 4858 for AlphaGo Master, and whereas 3739 for AlphaGo Lee and AlphaGo Fan. Finally, we ranked AlphaGo Zero directly as AlphaGo Zero. Complete 100 game matches using a 2 hour timer. AlphaGo Zero won 11 games in 89 games. It also competes against the strongest extent program, AlphaGo Master, and based on the algorithms and architecture shown in the document, but with the human data and functions. See, they are the methods like this, and is the strongest online, and defeated a game professional player at 60 minutes. The game was defeated in January 2017-34. It was in our assessment. All programs allowed 5 seconds of thinking timer per move. AlphaGo Zero and AlphaGo Master were played on a single machine with 4 TPUs each. AlphaGo Fan and AlphaGo Lee were distributed on 176 GPUs and 48 TPUs respectively. It also includes players based slowly on AlphaGo Zero's raw neural networks, and the player simply choose to move with the highest probability. And finally, coming to the conclusion, the learning approach is perfectly feasible even in the most difficult cases domain. It is possible to train at the superhuman level without humans examples or instructions. When knowledge in the field does not exceed the basics rule, you also need a pure reinforcement learning approach. Achieve much better asymptotic analysis in few hours of training performance compared to training using human expert data. With this approach, AlphaGo Zero defeated the previous strongest version. AlphaGo is trained far away from the human data with handmade features. Mankind has accumulated Go knowledge from millions of games. It has been played for thousands of years and distilled into patterns, sayings, and books within a few days. Within a few days, Tabula Rasa will begin. AlphaGo Zero was able to rediscover much of this Go knowledge as well as Rome, a strategy that provides new insights into the oldest of all games. And thank you.